Point four, harmonic motion. Alright, we can use the cosine to describe regular simple harmonic motion here. Let's assume that we have some kind of board up here, okay? We have a spring and an object attached to the spring. And then we can pull the string down and we can let it go and so forth, okay? And what's going to happen with that spring, it's going to oscillate back and forth. Alright, let's suppose that I pull the spring down, or let's suppose this object's heavy enough, okay? And then I release it, and then it bounces down, bounces up, bounces down, bounces up, and so forth, okay? I can describe the position where that object is at between negative A and A by using the cosine function, okay? Because what's going to happen? It's going to go down like this, then it's going to go down to here, then it's going to spring back up a little more and spring back up. And as you can see, that follows what? The cosine function. If I look at it as the position or the vertical position of the object versus time, okay? All right, it can be modeled by this. Y is equal to A cosine of omega times t. Now, we're used to seeing bx, but it's no different, really. All right, let's suppose that instead of A to negative A, maybe I had like some numbers here, like say 10 to negative 10, 10 to negative 10. And this t value right here would start at 0, and this t value is maybe a half, okay? And I wanted to come up with the cosine function for this. Well, we've done this before whenever we looked at the regular cosine function. If I want to come up with the cosine function, y is equal to a cosine of omega times t. What was this a? This a stood for the amplitude, right? So what would the amplitude be in this picture? Be 10 times the cosine of omega times t. Well, what was this? This came from the period, this omega part. What is my period of this cosine function? One cycle happens from 0 to 1/2, so the period is 1/2. And how did we calculate the period? We said that it was what? Pi, or 2 pi over b for the cosine function. So the period, which we just said was 1/2, is equal to 2 pi over b, and we get b is equal to 4 pi. So in other words, we have omega in the place of b, but it's still going to be the same number, 4 pi times t. That would be my function to model what? The vertical position of this object at a certain time period. Alright, so if you look at your notes, next, you have a whole page of stuff that talks about simple harmonic motion and so forth, okay? I want to focus on a few things here. Well, if the displacement d of an object at time t is given by, so sometimes we'll model simple harmonic motion by, come down here, d is equal to a times the sine of omega times t. And sometimes we'll model it by d is equal to a times the cosine of omega times t, which we just saw an example of this one, okay? It depends on which curve it fits better, you model it off of. Alright, then the object is said to have simple harmonic motion. Okay, the amplitude is the absolute value of A. I don't think I need to write that down. Period is going to be 2 pi over omega. In other words, you find it the same way we did back in the cosine function whenever we're graphing that section. But you're going to use omega instead of b this time. Alright, now they talk about something new, frequency. The frequency they're calling lowercase f is equal to 1 over the period, or we could say the reciprocal of the periods. Alright? And that's the time required to complete one cycle, it says. And it also is measured in hertz, Hz. It's going to be the unit for it. Alright, so that talks about the what? The equations we use to model the simple harmonic motion.